Hello. Today I'm going to be presenting on the rebounding capsule. I'm Ilo Chen, and my teammates are Wu Zheyu and Zhenzhong Rei. So the problem statement states that a spherical ball dropped onto a hard surface will never rebound to the release height, even if it has an initial spin. A capsule-shaped object, for example a tic-tac mint, on the other hand, may exceed the initial height. Investigate this phenomenon. So first off, I want to make a comparison between a spherical ball and a capsule. Then I want to talk about the mechanics that allow the capsule to exceed its initial height, and finally investigate the relevant parameters. So here is my structure. First off, I'm going to talk about my experiment and my preliminary observations. Then I will move on to my qualitative explanation of the phenomenon and the quantitative explanation. Finally, in the conclusion, I will talk about the physical significance of this problem. So here's my experimental setup. You see we have a guided release system and a double camera system to make sure that the motion is confined to a single plane, and we use 3D printed capsules of different sizes. So here is a quick demonstration of our experiment. From our demonstration, we can move on to some simple motion analysis, where we assume that the only forces that the capsule experiences during free fall and after the rebound is gravity. Therefore, we can list out some equations of motion and find the final height h prong as dependent on the vertical velocity after the impact, and the distance between the center of mass and the ground during the impact. Using tracker, we have the motion analysis in the x direction, the y direction, and we obtained the angular velocity by dividing 2 pi over the averaged periods of rotation. After finding the velocities in the different directions and also the angular velocity, we can obtain the energy of the system. After graphing the energy of the system before and after the impact for various different experiments, we realized that this is an inelastic collision and that energy is lost during the impact. We also make the connection that in order for height to increase, vertical velocity must increase, which means vertical translational energy increases, which corresponds to a decrease in rotational energy, as we can see from our experimental data. So that must mean that some force and some torque are doing work on the system. So this leads us to want to draw a free body diagram. For our theory, we use the impulse momentum theorem, in which a force doing work over some time corresponds to a change in some certain mass's velocity. So in the vertical direction, we realize that this corresponds to the average normal force. And therefore, our theory is that for a greater average normal force, there should be a greater rebound. So this leads us to form our theory about the impact velocity and the impact angle. The impact angle here we have defined as beta, as you can see on the left. So for ranges of beta between 0 degrees and 90 degrees, the angular velocity will actually create a vertical component for the contact point, which means that the impact point actually has a velocity v(imp), which is equal to the velocity of the center of mass plus d times omega times sine beta, which is greater than the velocity it would have actually had if it was only due to the velocity of the center of mass, and therefore that's what it gives it a greater normal force. So here is our qualitative explanation. At certain impact angles, the impact point has additional vertical velocity due to angular velocity, and that creates a greater normal force, which imparts a greater vertical momentum. The capsule leaves the ground at a greater speed than it landed, and the rebound height exceeds the initial height. So to make sure that our theory is largely correct, we did some preliminary experiments to check. So here we have an experiment about the average normal force and the impact velocity, and we see that it's largely a positive correlation, in which when the impact velocity is greater, it corresponds to a greater normal force. And also, to talk about the angle of collision, we define the coefficient of restitution to see if the theory checks out. And as you can see, the coefficient of restitution, which we have defined to be the square root of h prong over h, which is the final height over the initial height. The coefficient of restitution only exceeds 1 at certain impact angles between 16 degrees and 75 degrees, which largely fits our theory. And also, this can also talk about why a capsule and a sphere have different rebounding motions. Because for a sphere, the angular velocity always creates a velocity component in the horizontal direction, and therefore it cannot generate a greater normal force. And now we move on to our quantitative explanation, in which we consider an inelastic collision model. And here off we model the contact point as a spring with dampening, and therefore the total normal force experienced is the force of the spring and the dampening force. And here we have the fixed equations of motions to account for the forces doing work on the system. And here we have used the simple geometries of the capsule to obtain relationships between the y direction and the x direction, and also between sine beta and cosine beta. And here on the right side, you can see that we can list out the equations for the vertical velocity, the horizontal velocity, and the total torque, which corresponds to an angular acceleration. Now we move on to our simulation model. So our inputs are the velocities in the y direction and the x direction of the center of mass, the angular velocity, and the impact angle. From these, we can obtain the vertical velocity and the horizontal velocity of the contact point. After a small time step, these will generate a small movement in the y direction and the x direction, which corresponds to creating the creation of a normal force and also the frictional force and also a torque. Now, using these and the previously obtained equations of motions, running them for a small time step again, we can obtain the new results for Vy, Vx, omega, and of course theta. And this also corresponds to a new delta y and a new delta x. Now we continue to run our simulation until the capsule has departed from the ground. So here are the impact predictions from our model. So here you can see we can form a graph of the average normal force, and we can also form a graph of the velocity and how it transitions during the impact. And you can see the vertical velocity largely fits with our experimental data. Now, in the x direction and in the angular velocity direction, there are deviations, but the deviations are small enough that it is largely able to predict the motions. So here are the relevant parameters that we obtain using our simulation. So the radius of the capsule and the length of the cylinder affects the mass of the capsule and the moment of inertia, which will affect the distribution between rotational energy and translational energy. So we notice that for our capsules, when the radius increases, the mass increases more than the moment of inertia, and therefore the energy is largely in the vertical translational energy, and the rotational energy cannot impart as much energy, and therefore we have lower rebounds. However, if we increase the length of the cylinder, the moment of inertia increases much more, and therefore we see higher rebounds. So in our conclusion, the phenomenon occurs because rotational and translational energy transfers during the impact. The normal force is responsible for creating a greater vertical velocity. Certain impact angles have greater impact velocity and therefore greater normal forces. The impact can be modeled with a hypothetical dampened spring. And here we have our additional references in which we used GeoGebra to obtain the contact point and the contact time. And also, these are the calculations for our moment of inertia of the capsule, in which we calculated it as different half spheres and a cylinder, and then we used the parallel axis theorem.